Hi everyone, this is Kalyan Kumar this side, and welcome back to Chemistry Universe. This is the part 2 of the electrophilic aromatic substitution videos. And in the previous one, we talked about the what basically electrophilic aromatic substitution is, what is an electrophile, what do you mean by aromatic substitution. We also talked about the basic reaction mechanism. All the reactions of electrophilic aromatic substitution follow a certain basic principle, which we discussed in the last video. And there would be a bit of change in certain reactions, but it won't change drastically. Probably the only step that would differ from one reaction to the other is the production of the electrophile. And then we also talked about, what is the rate determining step and how do we determine the rate determining step and why is that the rate determining step. We talked about all of that. So if you haven't watched that video, I'll put the link of that in the description below. So make sure that you watch that video. Now, in this video, you'll also be presented with a lot of questions. And I would want you to make sure that you copy those questions and then you pause the video, copy all those questions, and then work out all those questions, and then play the video back to get the answers. That is the way it should work. So take it as a classroom, and this is what I keep repeating in all my videos. So without more delay, let's get on with the video. This is part 2 of electrophilic aromatic substitution, and this is titled reactions. All right, here we go. So the first reaction that we're going to talk about is called halogenation. As the name itself signifies, we are going to put a halogen on benzene. So halogenation of benzene is carried by reacting a halogen molecule with benzene in the presence of catalysts, which are Lewis acids such as FeCl3, AlCl3, etc. So the basic reaction looks like this. So what has basically happened is that out of the two chlorines, one chlorine is attached itself to this carbon atom, and the hydrogen of this carbon atom has gone with the other chlorine to form HCl. So that's what has basically happened. Now let's check out the mechanism. As I said, we already discussed the basic mechanism for all. Probably the formation of the electrophile will differ from one reaction to the other. Now in step 0, which if you remember the last video, we talked about step 0. This is the formation of the electrophile and base. So we have a chlorine molecule, and I'm showing you one of the lone pairs of one of the chlorine atoms. Now FeCl3 is a Lewis acid. Now this helps in the formation of the electrophile Cl+. And how does it do that? The lone pair attacks the Lewis acid. You get an intermediate like this. And this Cl positive, pulls the electrons towards itself. And the pulling would be so great sometimes that it would snap. It will break, giving you Cl plus and FeCl4 minus. This is the base, while this is the electrophile. And if you remember, we need both of these two. Now here I would like to interject that, we will be doing hydrocarbons. In fact, in hydrocarbons, you will notice that the alkenes, which are very similar to benzene and other aromatic hydrocarbons in that they have a pi electron cloud, alkenes do not need the Lewis acid to get the electrophile. So the same reaction you will see in alkenes, of course, it will be an addition reaction. It won't be a substitution reaction there. The same reaction you will see in alkenes, but here you will notice in the case of alkenes that it doesn't need a Lewis acid simply because the pi electron cloud of alkenes is exposed. So it can polarize the Cl2 into Cl plus and Cl minus on its own. Whereas in benzene and other aromatic compounds, you'll find it's a closed loop. The pi electron is a closed loop that decreases the surface area of the pi electron cloud, which will make it less electron rich as compared to an alkene, and therefore they are not able to polarize the halogen molecule on their own. They need the assistance of a Lewis acid to do that. All right, so now Let's look at step one, pretty simple. We have benzene, we have Cl plus. Pi bond moves to one of the carbon atoms, attacks the Cl plus, and you'll get this rhenium ion intermediate. And in step two, the rhenium ion intermediate reacts with the base. The base takes the proton, and you get the intermediate again becoming aromatic, leaving FeCl3 back, the catalyst again, and you'll get these two. So basically, we have substituted, okay? Now let's look at the halogenation of chlorine, bromine, and iodine difference. Now the halogenation can be done for Cl2, Br2, and I2. Fluorination is not possible as the electrophile F plus is very unstable and is not produced easily. Now iodine is weakest of the three halogens, and even in the presence of a Lewis acid, it can halogenate reactive aromatic ring only. So what it basically means is if you simply react I2 with benzene by the same mechanism, you're not going to get good yield of the product. It will remain in equilibrium. It is very less reactive I plus. So unless or until you have something that makes benzene highly electron rich, like a releasing group, only then you can do iodination. Simple benzene, it's not going to be a good yield product. Therefore, in most cases, iodine monochloride is used in the presence of Lewis acid, like ZnCl2. So what we are saying here is that instead of using I2 with FeCl3, which is not going to be productive, we use ICl with zinc chloride or FeCl3 or any other Lewis acid. This will help because this will attack here and this will go and you can easily get I plus, whereas it's not easy to get it from simply I2. All right, let's move on to the next reaction. Nitration is the next reaction. Now, nitration is the reaction in which you're going to put the NO2 on benzene. So you have a benzene and you take out one H and you put NO2, a nitro group on it, and we get nitrobenzene. So nitration reaction is generally carried out with a mixture of concentrated nitric acid and sulfuric acid. The reagents which cause nitration are called nitrating agents. So you have this, you have HNO3, you have sulfuric acid here, which is the catalyst by the way, and you have NO2 sitting on benzene, and you have H2O. So let's see the mechanism. And here again, the formation of the electrophile will be quite interesting. This is HNO3, okay? And this is sulfuric acid. Now, I've mentioned this before, especially in alkyl halides, that what happens is, when two substances react and they have acidic H, one can give the acidic H to the other. And if both of them have it, then the other can also give acidic H to this. Both ways it's possible. Yes, one way would perhaps be more, that is, a stronger acid would be able to give the H plus much more easily than a weaker acid, but both reactions would happen, number one. The second point is that there may be multiple positions in a molecule which can take an H plus. Basically, to take an H plus, you need an atom with a lone pair. So if you have multiple atoms with lone pairs, then the H plus can go to any one of those. Obviously, it will go to perhaps one type of site more easily than the other. But when we are doing reaction mechanisms, we are not actually bothered about where the H plus is more likely to go. We are more interested in where it will go and the reaction will happen. So we will only put the H plus in that place where the subsequent reactions can happen, because ultimately they do happen, right? I mean, all of these reactions that we are talking about, they do happen. We are not making them up. So the fact that they happen implies that the H plus must have gone to that particular site. Now, it may be less likely to go there. It may be more likely to go there. It doesn't matter. But it is ultimately going there, and only because of which the reaction is happening. So when I show you that the H plus has gone to a particular atom, it does not imply that is the most likely place to go. It only implies, well, the reaction is going to move forward only when this happens. Yes, it can keep exchanging H plus with the other atoms as well. That is also possible. But once the H plus goes there, subsequent reactions can also happen. All right. So here what happens is sulfuric acid, being the stronger acid, is able to give the H plus to HNO3, and you will get the protonated HNO3. Can you notice here that sulfuric acid is acting as an acid, whereas nitric acid, HNO3, is acting as a base because it is receiving H+. Now, one might feel a little odd in calling nitric acid as a base here, but then in the presence of a stronger acid, perhaps it is acting as a base. After all, it is taking the H+. Now, let's see what happens. Now, OH2 plus is a good leaving group, and you get HSO minus, and this is the base. The OH2 plus is a good leaving group. It will leave as water, and you get the electrophile NO2 plus. And these are the two things we need. And step 1 is the same. Electrophile is being attacked by benzene, arenemine. Step 2, the arenemine reacts with the base, takes the proton, and you get the aromatic thing, nitrobenzene. And the sulfuric acid is generated back, which is why we call it a catalyst. So as we realize, sulfuric acid is acting as an acid while HNO3 is acting as a base. Now, instead of this, we can alternatively use other nitrating agents also. For example, we can use HNO3 without sulfuric acid, in which case HNO3 has to be concentrated. N2O5 with sulfuric acid. We can even use a solution of NO2ClO4 and NO2BF4. Now, as far as these two are concerned, it's pretty simple to understand why we are using them, because they are the salts. And they are made up of basically NO2 plus and ClO4 minus. So this is the electrophile and this is the base. In the case of NO2BF4, well, you have NO2 plus and BF4 minus. You have electrophile here and base here. So it's pretty easy to understand why we use these. But let's also understand what happens when you use nitric acid alone and when we use N2O5 with H2SO4. So what happens there? How do we get the electrophile? So let's check out that mechanism. So again, step 0 for those. This is pure nitric acid. Now basically what happens is one nitric acid protonates the other. And again, we come back to the same stuff. How can one HNO3 protonate the other? The question should not be why it should. The question should have been why it should not had it not done that. Because giving H plus is, it's not that the acids or the bases already know which is more acidic, which is less acidic. They just keep interchanging whatever they can. So molecule A can give it to molecule B. After a while, molecule B can return it. Then molecule B can give it to molecule A. These things can keep happening. Yes, in doing so, if something else happens, if the reaction goes in another direction, that's a different story. But protonation can happen between two similar molecules. Like for example, the ionization of water. You write 2H2O giving H3O plus and OH minus. What is that? That is one H2O protonating the other. So this type of behavior is expected between molecules. All right. So the same thing occurs. You get the protonation and you get NO3 minus. NO3 minus is the base. And water leaves. You get electrophile. In the case of N2O5, this is what happens. Sulfuric acid. Let's say the middle O gets protonated. You'll get something like this. One of the bonds will break between nitrogen and O. This part, the one that is breaking, this will become HNO3 and this will become the electrophile NO2 plus. So basically you're going to get HNO3 and NO2 plus. And this HNO3, because you're using sulfuric acid, can further nitrate. It can again produce another NO2 plus. So it's almost like with one N2O5 you can get two NO2 plus. So this is the electrophile. So now let's look at the third one, that is called sulphonation. Now unlike the previous two, where you got halogenation and you did halobenzene, like chlorination you got chlorobenzene, nitration you got nitrobenzene. In sulphonation you don't get sulfobenzene, you call it benzene sulfonic acid. So basically what happens is here the benzene is going to be substituted, the H of the benzene will be substituted by SO3H, and which when attached to benzene will be called benzene sulfonic acid. So sulphonation is done by heating the substrate with concentrated sulfuric acid or fuming sulfuric acid containing various proportions of sulfur trioxide. So basically fuming sulfuric acid is similar to oleum and you have various amount of SO3 is present in sulfuric acid. So basically the reaction occurs with SO3. SO3 is the electrophile, perhaps the first encounter with a neutral electrophile. and sulfuric acid behaves as the catalyst here, and you get SO3H. Let's check out the mechanism, similar to the previous ones, but again, the interesting part will be the step 0. So basically, sulfuric acid reacts with water to produce HSFO minus and H3 plus. It gives H plus to water. Now remember, this is not the formation of the electrophile, even though in all other previous cases, step 0 was the formation of the electrophile. Here it does not, because the electrophile is already there, it's SO3. Now you might wonder, why am I showing the step 0? You'll understand later. Step 1, benzene reacts with SO3. So pi bond moves, carbon attacks the electrophilic sulfur, pi bond again moves to oxygen, and you will get intermediate, rhenium ion. Step 2, the intermediate loses the proton to HSFO minus, and you get sulfuric acid leaving off, which is why it's a catalyst, and you get benzene sulfonate ion. But remember, this needs to be protonated, and that's where this H3O plus comes into the picture. So the benzene sulfonate reacts with H3O plus, giving off water and producing benzene sulfonic acid. Now, all these three reactions are actually in equilibrium. Okay? And sulfonation differs from other reactions in a significant way. Now, sulfonation is different from other aromatic substitution reactions. Firstly, it is reversible, and secondly, it shows some amount of isotopic effect, the kinetic isotopic effect, which is totally absent in other cases. So you need to understand something. You know, when we talked about kinetic isotopic effect, when we did the part 1, in the part 1 I said, in the general mechanism, generally electrophilic aromatic substitutions do not show kinetic isotopic effect because it is the step 2. You know, this is the step 2, which is the fast step, in fact, because it is gaining aromatic character. So the loss of H is not going to, if you change H with a D, it's not going to make much of a difference. But what you also need to understand is that this reaction is a reversible reaction. So in a reversible reactions, what actually happens is that, this step, the second step, remember the first step is also reversible, right? In fact, this will be more reversible because you get an rhenium ion. Now, the rhenium ion has two options. Either it loses the SO3 and forms the reactant by going back in the first step, or it loses the H plus to form the product. So these are the two possibilities that the intermediate has. Now, which one will occur will depend upon which reaction is obviously faster. Now, the reverse of the first and the second forward, these are the two competing reactions now. Generally, in all previous examples, halogenation, nitration, you'll always find that the second step is far faster than the reverse of the first step. Meaning, the intermediate has a greater chance of losing a proton than the electrophile, because the electrophile is unstable in those cases. Cl plus, NO2 plus, they are all having positive charge on a highly electronegative element which is not stable. So the intermediate prefers to give H plus rather than the electrophile back. But SO3, if you remember, is a neutral electrophile. So it's not that unstable. And therefore, it has a very good chance of going back to the reactant. That means the second step is not the fastest step. In fact, it is very possible that the reverse of the first step could also be faster than the second step. So giving off H plus may be slower than giving off SO3. So in that case, what happens is when you replace the H with a D, there will be some fluctuation in the rate. And that is what we call as the kinetic isotopic effect, which we also discussed in alkyl halides. Okay, so this is the reaction profile. So reactant going like this. This is the reactants. This is the first TS where the SO3 is just attaching itself, partially attaching. This is the intermediate. And this is the transition state of the second where H is leaving. And this is the product. Now you do notice that this second forward and first reverse have almost similar activation energies. So now they are comparable. Meaning if I change the H with the D and T, this can go even higher. And if it goes higher, then this will also have some impact on the rate of the reaction. So we see that once the sigma complex benzenium intermediate is formed, the energy barriers on either side of the intermediate are roughly of the same magnitude. This means that the intermediate can cross over to the product and it can also come back to the reactant. This accounts for the reversible nature. But the moment I put a different isotope, now this reaction we saw for the CH. Now this would be for CD, this would be for CT. Why? Because the CH bond will be weaker than the CD bond. CD bond will be weaker than the CT bond. And therefore, it will be difficult to break them. So if we have deuterated substrate, then the potential energy diagram gets slightly modified, the red curve. The barrier to step 2 becomes higher as it now involves the cleavage of the CD bond. The barrier for step 1, on the other hand, remains the same as the sigma complex because it is going back to the, since the H or D is not involved in the reverse of the step. This is not involved here. It's only involved in the second step. So the rate of its reverting back to reactants is higher than its crossover to the product, which is why there is some type of kinetic isotopic effect. The next one, very interesting, Friedel-Crafts alkylation. This is where you put an alkyl group on benzene. Friedel-Crafts alkylation is a reaction in which benzene is converted to alkyl benzene. So you have a benzene, you have a RX, you have AlCl3, and then you have an alkyl group on benzene and you have HX. So let's understand how this is done. Mechanism. Again, electrophile is very important. How it's formed. Step 0. So if you have RX, of course, this is not the only way you can do it. There are other ways of producing electrophile. This is one of the ways. And you take a strong Lewis acid like AlCl3. Just like halogenation, the Cl plus will pull the electrons and you get an intermediate like this. This is a complex. And then eventually the complex breaks depending on how stable the carbocation is. If the carbocation is highly stable, then perhaps this reaction would be faster. The complex will not remain for a larger time. And you get the electrophile here and the base is this one. So let's see what happens in step 1. Benzene, you have the electrophile. Pi bond moves to the carbon, carbon attacks the C plus, and you get this. And don't have a problem with ET because this is basically ET, ethyl group. So you get the areneamine, step 2, areneamine will now react to the base. These Cl-Al bond breaks. This takes the H and this goes here and you will get AlCl3 released and you will get ethyl benzene and HCl. Now, remember, with Rx is a primary halide. In fact, it should be when Rx is a primary halide, a simple carbocation probably does not form. Instead, the AlCl3 forms a complex, and this is that complex. Okay? So the AlCl3 simply forms a complex with the alkyl halide, and this complex acts as the electrophile. So this part of the complex acts as the electrophile. In the complex, the carbon-halogen bond is nearly broken and one in which the carbon atom has a considerable positive charge. Okay. Now, the electrophile can also be produced in the following ways. RCl and AlCl3 is not the only way. You can have an alcohol with a strong acid like sulfuric acid or HF. That can give you an R+. You can even have an alkene with a strong acid like sulfuric acid or HF and you can get a carbocation. Generally, HF is not preferred. We will prefer sulfuric acid as it's a good dehydrating agent. So now comes a very important part. This is where I'm going to give you questions. You have to note down the questions. I'll show you in one particular slide. I'll show you all the questions of that particular slide. And you pause the video then, freeze the video, pause the video, and then you note down all the questions, get your answers, and then compare it, and then play the video back and then compare your answers. That is the way it should be done. Okay, so let's look at some examples now. Now, in the case of examples, first one, let's look at this one. You have a benzene and you have this guy here with AlCl3. So don't pause it now. Let's see all the questions. So this is the second example. This is example 3. So now I would want you to pause the video and make the structures and play the video back. So now let's look at the first one. So I hope you have made the structures now. So let's play the video. Now what happens is, of course, obviously AlCl3, you'll get some kind of a carbocation here. And then you expect, remember, carbocation rearrangement occurs. So hydride shift will make the carbocation here. Then another hydride shift will make the carbocation here. So basically it is this carbon that will be attached to benzene, meaning you're going to get something like this. So I hope you have made this, and remember, in every case I'm only asking the major product, so just look for the most stable carbocation after rearrangement and make sure that that gets attached to benzene. So I'm sure you must have done the second one. The same logic applies. Primary carbocation, hydride shift, secondary carbocation. Now here this carbon does not have a hydride, it has a methyl group. So there's a methyl shift and you get a carbocation here, meaning you get something like this. So just check your answer. So just check your answer and see whether it's working out. Now the next one, I'm showing you this as the product. Same logic applies. You get a carbocation here. You have a hydride shift. You get a carbocation here. Now out of the pH and the CH3, you will have a phenyl shift, meaning you get a carbocation here. And is this carbocation that should be attached to benzene. Now what you may see in the product is something different. You may see that, okay, this should be attached to benzene. There should be a phenyl shift. This should attach to benzene. But here that is not attached to benzene, right? I mean, shouldn't this have two CH3s or something? Well, that's the problem, The problem is that you can be given options like this, and this is where you will falter. Remember, there's a phenyl shift. Carbocation here. This attaches to benzene. Now, I've made that benzene as pH. And the one that I've shifted to the carbon, I've made it like benzene. Now, this is where you have to be careful. Now, generally, we have this tendency that, whatever is drawn as benzene is the one that was initially drawn as benzene. No, it's not necessary. If the other reactant also has a benzene ring, I could have drawn that as benzene ring. And this is where you will get confused in an answer. So be very careful with this. Some more examples. Again, note down the examples and then pause the video, make your products, and then check out. So pause the video now, make the products, and then play the video back. So I hope you have made the products. The first one is pretty simple. This is going to be a secondary carbocation here. And remember, when you remove OH, you have to remove with the bond. Don't let the bond remain because the bond is with OH. If OH goes, the bond goes. So this carbocation is attached to benzene. And again, don't, some people have this tendency that, they will make benzene, then they will put a 6-membered ring like this with a carbon atom common. There is no common carbon atom. This carbon atom is different from this carbon atom. There is a bond between them. Number of carbons has to be maintained. Now, in the second case, obviously, it's pretty simple. Carbocation secondary, there's a hydride shift, and this gets the carbocation. And finally, this is attached to benzene. Next case, I think the carbocation is pretty simple. Here, it's already the tertiary that is formed, and that itself will be the product. In the next case, it is going to be similar. You get a primary carbocation, then you have a hydride shift, you get a tertiary carbocation, and you will again get the same product. Let's look at some more examples. And just note down these and draw the products, major products, and then play the video back. Pause it now. So I hope you have made it. Again, a carbocation is formed here. This is secondary. There is no scope of rearrangement. So a 5-membered ring is attached to benzene. Here again, the carbocation is formed in the tertiary place. You get this product. Again, you get a carbocation here. And remember, I don't know if you have thought about this. There is no ring expansion here or here. Because ring expansion can only occur in a 5-membered ring if the plus is outside the ring, not on the ring. Here, as you can see, the plus is outside the ring. And there would be a bond breakage of the ring. It will attach itself here. You will get some kind of a plus here. And eventually, you will get a 6-membered ring attached to benzene. The same happens in the next case. Carbocation is here. Primary. Then this bond breaks. You will get a 6-membered tertiary carbocation, which will attach to benzene. Let's check out some more. So, make these and pause the video now. There are only 2 examples in this. Pause the video now and make the products and then play it back. So here again, it's a 6-membered ring and the positive is outside the ring, but this is not going to expand. A 6-membered ring never expands to 7-membered ring. So basically what will happen is a methyl group, since it doesn't have an H, this methyl group will shift to this carbon atom and this carbon is attached to benzene. So you are going to get something like this. Now if you have a problem in understanding, pause the video, again try and make on your own based on what I said and check this. Now here what happens is you get a carbocation here, secondary. Now this is the adjacent carbon where the carbocation would like to come because it will have more hyperconjugation. Now instead of a methyl shift, remember it's a 7-membered ring. 7 can contract to 6 and for contraction you need the plus on the ring. So this will break, this will join here. So what will basically happen is you had this 7-membered ring. Now these two are joined together to give you a 6 and there are these 2 bonds and there's a plus here. Just rub this out and join these 2 and you'll get it. So you have a 6-membered ring and a tertiary carbon. Now it has been noticed that when you change the catalyst, the product can be different. For example, in this case, it has been seen that if the catalyst is FeCl3, you do not get a rearrangement. You directly get a primary carbon attached. Whereas if you had used AlCl3, you would have got the rearranged one. And the reason for this is because FeCl3 is not a strong Lewis acid, it's a weak Lewis acid. So remember the complex that was formed? So the complex is a very weak complex and takes a lot of time for the complex to break into a carbocation. So with FeCl3, carbocation formation takes a lot of time and benzene molecules will tend to react with the complex more faster than, they're not going to wait around for the carbocation to form. So what will basically happen is that they will start reacting with the complex itself. Whereas in the case of AlCl3 being a strong Lewis acid, will form the complex faster, will make it break it faster and sort of you get the carbocation pretty fast and you'll get more of the rearranged product. Because once the carbocation is formed, then rearrangement is highly likely. So this is explained by the difference in the acidic strength of FeCl3 and AlCl3. FeCl3 is a weak Lewis acid compared to AlCl3. On reacting with the alkyl halide, the coordinate bond formed between halogen atom and Fe is not very strong. Due to this, the carbon-halogen bond does not break immediately. The bond cleavage occurs slowly. So with FeCl3, the reaction occurs through the complex rather than the carbocation, something like this. But it has also been observed that if you use AlCl3 but temperature is low, then again there is a non-rearranged product. If the temperature is low, then even with AlCl3, the major product is non-rearranged, suggesting that low temperature is not conducive for the carbon-halogen bond cleavage. Alright, now we have the last of the electrophilic reactions that is called the Friedel-Crafts acylation. Similar to alkylation, but here you're going to get aromatic ketones. So, and it is always said that, acylation, Friedel-Crafts acylation is a much better way of producing alkyl benzenes than alkylation itself. Now, alkylation has a problem because if you don't want the rearrange, first of all, it will rearrange if it is possible. And if it is going to rearrange, then the product yield is going to be low. Now, acylation is better because there is no rearrangement here that you will see. But again, the product is ketone. So how do we convert the ketone back to the hydrocarbon? So I'll show you some reactions for that. Okay, the Friedel-Crafts acylation reaction is an effective means of introducing an acyl group, that is the RCO group, into an aromatic ring. The reaction is often carried out by treating the aromatic compound with an acyl halide or anhydride. This is acyl group, okay? This is acyl group. And when it is attached to halogen, we call it acyl halide. And if this is attached to like this, it is called anhydride. So these are the two substrates that we can use along with benzene. And obviously you have to use a Lewis acid again. So benzene, acid chloride, and reaction with AlCl3, you have the same thing with anhydride, and the product is the same. And this is what you get in both. But of course, in this case, the H will go with the Cl. And in this case, this bond breaks and this comes on the carbon. So the H of this carbon will go with the H of with the O of this and giving you a carboxylic acid. This is pretty important. Mechanism. Well, step 0 is the key. RCOCl, AlCl3, very simple. You can understand this breaks. You get the acylamine. And this is the base. While with anhydride, well, this attaches to this Al. And you get this. Then the CO bond breaks. You again get the acylamine. And this is the base. So depending on the substrate, you get two different bases. Now, if I take step 1, acylamine, pretty simple. You can understand this. Step 2. Now, I'm going to show you step 2 in both cases, okay? I'm going to show you step 2 when this is the base. And I'm going to show you step 2 when this is the base. So, first with this thing, AlCl3, and you can understand HCl is formed and the ketone is formed. Whereas if I were to show you with the other base, you'll get a carboxylic acid. And this breaks, the O attacks the H, it goes here, you get the ketone, and you get the carboxylic acid. Now, the reason acylamines don't undergo rearrangement is because they are highly stable. And they're stable because of resonance. Acylamines don't undergo rearrangement, they are stabilized by resonance. If you look at this, the lone pair of O, the octet gets completed. And we have also noticed that if the alkyl group attached can produce a very stable carbocation, if the alkyl group is tertiary, the acylamine undergoes decomposition and alkylation takes place instead of acylation. Say, for example, if you have this acylamine, now you would expect this to attach to benzene. But what happens is this bond breaks. This bond breaks here. You'll get carbon monoxide and you will get, there's no O here. You get carbon monoxide and you'll get the carbocation, tertiary carbocation. Now, it has also been seen that in Friedel-Crafts acylation especially, the catalyst use AlCl3. Now, in all the previous cases, as we saw, the catalyst was always formed at the end, which is why we are calling it a catalyst. But here, AlCl3 is not a true catalyst because even though it gets released, as you saw in the mechanism, it gets released, but somehow you have to end up putting a lot of catalyst. In fact, you have to just treat it like a reactant and put as much catalyst as the reactants that you have. That is because the AlCl3, which is the Lewis acid, the product is a ketone, remember. The aromatic product is a ketone, and you have AlCl3, ketone has a O has a lone pair. So AlCl3 ends up bonding with the O by a coordinate bond and it gets stuck. To make it get unstuck, you have to hydrolyze it. So when you hydrolyze it, the AlCl3 is lost. It becomes AlOH thrice. So ultimately, the AlCl3 is consumed just like any other reactant. So in Friedel-Crafts acylation, the catalyst has to be used in large quantities, though it seems to be produced in the overall reaction. This is because the catalyst formed at the end forms a coordinate bond complex with the carbonyl product. Something like this, as I said. To isolate the product, we need to hydrolyze the above complex. In that process, the AlCl3 converts to AlOH thrice and the catalyst is therefore lost. Now I'm going to give you a set of reduction reactions. Now, these are not part of electrophilic aromatic substitution. The reason I'm giving you these set of reactions is because I'm going to give you a sequence of reactions based on electrophilic substitution, which will involve these reactions also. And you'll be able to do them only when you know these reactions. So for the time being, without going into how and why and etc., just note down these reactions, remember them. We will do them at appropriate times. And once you do that, you'll be able to, sort of do those sequences that I'm going to give you. So some of the reduction reactions that you need to know at this stage, just know them, are these. The ketone formed can be converted to a variety of compounds, including hydrocarbons. Therefore, acylation followed by conversion to hydrocarbon is a better way of doing alkylation than Friedel-Crafts alkylation, as there will be no rearrangement, as I said in the beginning. How do you convert that? Now, the ketone or the aldehyde, it could be an aldehyde or a ketone, can be reacted with zinc amalgam in the presence of HCl, and you will get a hydrocarbon. Both O's go away and 2H come. This is called Clemenson's reduction. This is called Clemenson's reduction. Okay, we will deal with this later when we do the formation of hydrocarbons. But if you take an acid and do the same stuff, nothing will happen. It only happens with aldehyde ketone. You take an acid chloride and do it with this, nothing will happen. Now, if you take a ketone and treat it with NaBH4, the NaBH4 will convert the ketone into an alcohol. So it's like saying that a double bond O, it provides one H to both atoms, O and carbon. That way you can remember it. Now, with acid, no reaction. Now, ketones can also become alcohols with LAH, LiAlH4, a very strong reducing agent. Same thing. But the advantage of LAH is it can also react with acids. And so again, the same logic, you have both O's going out and 2H coming in. Right now, you only have to remember these reactions. Whereas if you take an RCOCl, if you use PDBSO4 as a special catalyst, then you get an aldehyde. This is called the Rosenmund reduction. Right now, you just need to remember the reaction. Rosenmund's reduction. This we will do when we do aldehyde and ketone. All right, now that you know these reactions now, I hope you remember these and take time to remember these. Pause the video if you want. Now I'm going to give you a reaction sequence, okay? And the reaction sequence goes like this. You have this reacting with an anhydride. In the presence of AlCl3, it gives you A. Then we use zinc amalgam and HCl, it gives you B. Then I use PCl3, you get C. And if you are having any problem with PCl3, let me tell you that the job of PCl3 is to simply convert any OH group into a Cl group. So, in fact, if you notice, we've already done that in hydrocarbons. And then you have AlCl3 reacting with C to give you D. Then you have zinc amalgam and HCl giving you E. And then you have selenium and heat giving you F. Basically, selenium heat, what it does is it dehydrogenates. Any compound that has hydrogens, it can dehydrogenate that, provided after dehydrogenation you get a very stable product. And you'll understand this once you do this reaction. So I want you to pause the video now and make all of these products and then play the video back. So now let's get on with the A. So I hope you have done this, you made all the products. Now basically what happens is, if you want to do the first reaction, just turn the molecule around so that it becomes easier to understand what is happening. Remember, it's an anhydride. Now if you remember anhydrides, what we discussed was that in the case of anhydrides, this bond breaks, the carbon gets attached to benzene and the O gets an H. But in this case, these two R's are also connected, meaning that this carbon is attached to benzene and the O gets H and they're in the same molecule. That is the only difference. So what will be A? A will be this. So basically A is attached to the benzene attached to this carbon. This bond is broken. So I've just turned it around, flipped it. This is attached to benzene. And as you can see, this bond is this bond. This bond is this bond. This bond is this bond. And there's a double bond O. And this O gets an H. And that's what you get in A. Alright, so what is B? Zinc amalgam HCl, Clemenson's reduction. What does Clemenson's reduction do? It only reduces the ketone or the aldehyde and not the acid. And it reduces them to hydrocarbon. So this is B. Just check. What does PCl3 do? Well, PCl3 removes the OH and converts that into a Cl. We saw that in hydrocarbons. So, C. In fact, we have done Clemenson's reduction also before when we did the preparation of alkanes. Then we do D, because what will happen with AlCl3? With AlCl3, this bond will break and this will attach to carbon, right? That's what it does with RCOCl. CCl bond breaks and it attaches to benzene. Here it is intramolecular, especially because the formation of a 6-membered ring is easy. Now what happens when you do zinc amalgam HCl? You'll get this. Now when I do selenium heat, can you understand what will happen? It dehydrogenates. What it means is, it will take one H from here and H from here. Remember we did aromatization in alkanes. It's the same thing. It takes 2H from here, it takes 2H from here. That way it can make this ring also aromatic. That's what selenium heat does. Okay. Now what I want you to do is, I'm going to give you a very complicated, at least it looks complicated, it's not. I'm going to give you a very complicated kind of a sequence. And this is going to take some time for you to do. So again, first see the sequence. Don't be scared of the way it is made or the way it looks like. Every reaction is pretty simple. Take your time, make all of them. And once I've finished all the sequence, I'll tell you when to pause the video. Then pause it, make all of them, and then play it back. So here, now the difference is, I'm reacting benzene again with an anhydride, but this anhydride has a benzene component also. And the first sequence is the same. A, zinc amalgam HCl, B, PCl3C, AlCl3D, zinc amalgam E, and selenium heat F. So this is the first sequence. This you can very easily make. Again, remember, just turn this around, make this part on this side, so it will be easier for you. And then you'll be able to make A, B, C, D, E, everything. Now I'm going to give you something different. What I'm going to do is, I'm going to give you a new reagent. And I'm not going to tell you what the reagent is, and I'm not even going to tell you what it does. You'll have to figure that on your own. So if I put LaH on B, I've already showed you, in fact, B becomes D in one single step if you want, by using this new reagent called PPA. Now what PPA does, I'm not going to tell you. What PPA is, I'm not going to tell you. But you must have made B and D. So you would know what the reagent does at least. This is hint number 1. The hint number 2 is, if I put LaH on B, and you've already seen some reactions of LaH, just go and check them, you will get G. And G can be directly converted to E in one step using PPA. So that is the second hint that you get for PPA. And then what happens is, A, I react with NaBH4, it gives me H. The H further reacts with benzene and a PPA combination to give you I. I react with zinc amalgam HCl to get J. Now from A, again I can use LAH to get K, and K can become J with benzene and PPA combination. D can become L with LAH, and L becomes J again if I use a benzene and PPA combination. Now J on selenium heat becomes M, and I with NaBH4 gives you N. N with a benzene PPA combination gives you O, which on selenium heat gives me P. Okay, now let's go back to C. What I do in C is I put the PDBSO4 hydrogenation, which is the Rosenman reduction, to give you Q, which with zinc amalgam and HCl gives me R. So this is the combination. Now it looks very scary, but it's not. Pretty simple. Now you can pause the video, note this entire thing down, then make each one of those, and then play the video back, because now I'm going to show you the answers to this. Now A, as I said, is pretty simple. You just have to, I'll have to keep referring back to this particular slide. So get back to the, and by the way, C becomes also G. I think I missed out one with NaBH4. So it's not a big deal. You'll be able to know that. So I hope now you've made all the products, and I'm going to give you the answers now. So A is pretty simple. A, we have already seen. What you're required to do is you're required to just turn this around, turn this molecule on the left side, break this bond. This bond needs to be broken. The carbon attaches to benzene and the O gets the H. That's all there is to it. So you get this. This is A. Now what happens with zinc amalgam HCl? It becomes a hydrocarbon, right? And yeah, it becomes a hydrocarbon. But acid remains as it is. What will happen with PCl3? Obviously OH will become Cl. And what will happen with AlCl3? Again the same thing, CCl bond breaks and the carbon attaches to benzene. You will get intramolecular acylation. What will happen with zinc amalgam HCl? Same thing, hydrocarbon. Now what selenium heat does is, just assume that this benzene ring is like this, okay? So what it does is take one H from here and one H from here. It has to take even number of H so that it can get H2. So you have one radical formed here and one radical formed here. So with this pi bond, what will happen is this electron and this electron will form a bond, pi bond, and this electron and this electron will form a pi bond. So basically this entire thing will become anthracene. Okay. Now if you look at the reaction sequence, you will notice that B becomes G with LAH. Now B is becoming G with LAH. LH does what? It reduces an acid into an alcohol, right? So G will be this. And what happens? Now, if I put PPA in this, now remember the first hint that you got for PPA was B becoming D in one step. Now, if B were to become D with PPA, what do you think PPA does? Hasn't it removed an OH? Of course, the bond is also going. When I say OH is going, the bond is also going. It removes the OH and joins the carbon to benzene. Isn't that is what is happening to D? So what is PPA doing? PPA is removing OH and attaching the carbon to benzene. Okay, that is hint number one. Hint number two is that G becomes E in one step with PPA. Now, how is that possible? What does PPA do? Remove OH, join the carbon to benzene. Isn't that is what is happening? So we have figured out what PPA does. Okay, so now let's move forward. Let's go to H. Now H, you have put NaBH4 on A. Now remember, NaBH4 does not attack the acid, only attacks the ketone, converts it into alcohol. Now what I've done is I've put benzene and PPA. So what does this benzene and PPA do? Now PPA is only going to remove OH and attaches to benzene. So for this OH it's not a problem. This benzene is readily available very close by. But for this OH there is no benzene available, which is why I'm adding benzene separately. And the order of addition is also important, because I don't want this carbon to attach to a benzene of a similar molecule. You see, another molecule of this type, that also, see, this molecule itself is having two benzenes. I don't want this carbon to attach to another molecule of this type on their benzenes. I want it to attach to a separate benzene. So first I will put benzene, then I will put PPA, so that when I put PPA, benzene is readily available for that particular carbon. So what do you think will happen after H? Well, after H, if I put benzene PPA, won't I get this? Just check. Just check with H here. This is H. So isn't this carbon joining benzene? Isn't a new benzene attaching to this carbon? And that is all we have drawn here. See, I. Now I undergoes zinc amalgam and HCl to form J. Obviously the ketone becomes hydrocarbon. This is J. Now we have also seen that A with LH becomes K. Now remember, go back to A. Where was A? I think A was here. So A with LH, remember LH reduces both ketone and acid to alcohol. So what do you think would be K? Wouldn't K be somewhat like this? Acid becoming alcohol, ketone becoming alcohol. So what do you think will happen if I put benzene and PP in this? Wouldn't K become J? This attaches here. New benzene attaches here. Okay. Now D became L with LAH. Now what was D again? Go back to D. Now what will happen with LAH? Wouldn't this ketone become alcohol? And that's what it does. What do you think will happen to L if I put benzene PPA? Won't I again get J? This OH goes and this carbon joins with benzene. Wouldn't you get J again? That's what happened. And then let's check out M. What is M? Now M is J with selenium heat. Now J with selenium heat, it will again make this aromatic, isn't it? So it makes it aromatic. Okay. So the next is N. What is N? N is I with NaBH4. Now what will happen with this with NaBH4? Wouldn't the ketone become alcohol? What will happen with benzene BPA? Again a new benzene comes. What will happen with selenium heat? The middle ring will also become aromatic. You will get a lot of aromatic rings. And lastly, we have Q. Now, if you look at the reaction sequence, C with Rosenman reduction gave you Q. So Q must be an aldehyde. Remember, I told you? Acid chloride with PDBS4 and H2 gives you aldehyde. And Q with zinc amalgam HCl gave you R. Now, obviously, it's a hydrocarbon, so it's going to become like this. So, I hope you are able to compare all your answers with this. And that brings us to the end of this particular video. So, I hope you found this video useful and watch it as many times as you want. Pause it whenever you want. It will always be better if you watch these videos in one go. Because when you pause it and come back later, it's not like a movie that you don't have to recollect much. Here you have to recollect a lot of things. So better to watch it in one go, but anyway, it's up to you. But please make notes. Make sure that you make notes while watching the video and pause it as many times as you want. So I'll meet you in the next part, and this is Kalyan Kumar signing off. Have a great and wonderful day, and thank you for watching this.